All right, good morning, everybody. My name is Steve Sorge. I'm PAC International Sales Director. With me today is Mike Raley. He is our Head of Engineering and our acoustician here at PAC. And Mike is going to review the following presentation, Design Details for Good Acoustics. This is part 1 regarding wall applications. Go ahead, Mike, take it away.
All right, yeah, thanks, Steve. So as Steve said, I'm PAC's Director of Engineering, and just for a little bit of background, like my background is in acoustical consulting and acoustics. I worked as an acoustical consultant for 10 years, so I spent a lot of time looking at architects' drawings and looking at these kinds of details. And now for the past 4 years and some change, I've been here at PAC overseeing our testing, technical support, product development, all kinds of things like that, and doing these webinars. So today's webinar is Design Details for Good Acoustics. And this is part 1. This is specific to walls. There will be a part 2 where I will focus on floor ceiling assemblies. Release time of that to be determined. And then we'll see what, if you've got questions in here, if you've got questions about other kinds of details and stuff like that too, feel free to put those in. Maybe I have a part 3 that's just, the other bits and things. We'll see. So with that, let's go ahead and get into this. Where's my clicking? There we go. Okay. So, when you're working on a project, you've got some sort of specification, guidelines, code requirement or something like that for acoustical performance. And a lot of times that's in, for walls, it's in the case, in the stated as in terms of an STC, so a sound transmission class rating. And that's, code for multifamily dwellings. You might have that in government requirements for, courthouses, Social Security Administration buildings, those kinds of, places where you need speech privacy. Often you'll have STC requirements. Maybe it's in FGI guidelines for hospitals, hotels, Hilton, Marriott, Hyatt have their own brand standards that have STC requirements for walls, high performance schools, all of these, right? You'll see these things, these guidelines requirements that have STC ratings. And typically the way we deal with this, that at its most basic level is, we have some sort of wall assembly. That's what we're trying to use based off of fire and structure and acoustics and, construction costs, these kinds of things, right? We select a wall assembly, and then we go looking for a test report, an acoustical test report for that assembly that gives us that STC rating. And hopefully that test report shows that the STC rating is above, meets whatever our requirement is. And then we go on our merry way. But what does that acoustical test report really tell us, and what doesn't it tell us? So in the lab, when we go build a wall, and this picture here is in an acoustics lab. This is a wall that PAC had tested in the past. It is an idealized environment, right? So we are trying to control variables so that really all we're testing is a sound that's being transmitted through the partition itself, the main assembly. So everything's constructed very nicely. You can see here how all the screws are nice and neatly aligned, right? And this one's not fully constructed yet, so the perimeter would be sealed, often with some sort of acoustical sealant, and then also often some putty tape and things like that. And we'll do more sealant around that perimeter because we're not trying to test the perimeter in the lab. We're trying to test the sound transmission just through the main assembly. There's also no electrical outlets. There's no switches. There's nothing hanging on the wall. None of these kinds of things, right? That's the idealized situation that we test in the lab. But in the real world, we have all this stuff that we have to deal with, right? And this is what makes our spaces functional. So we have wall-mounted TVs, we have wall-mounted lights, we have decorative panels, hanging cabinets, electrical outlets and switches. Maybe we've got wall-mounted media cabinets, or we've got, floating nightstands in the hotel. We've got a headboard in our hotel that's attached to the wall, right? We've got doors, we've got windows, all of these other things that are in our nice, neat little perfect wall that we tested in the lab. And all of these things can affect the acoustical performance. Oftentimes, they're all sort of weaknesses in our assembly that can reduce its acoustical performance. So if the goal is to, in the real world, actually reduce the amount of sound that's transmitted from one space to the other, we've got to address all of these details, not just have some assembly that gets a particular STC rating. And it's all those details that we're going to talk about today. Well, most of these, there's a lot of details. So again, this is part 1, more to come. So before we dig into this, let's kind of break this down in some really simple concepts here to kind of help us understand this conversation when we're thinking about details. And my hope is that for, especially for the architects and contractors and others on here, I give you a little bit more sort of some tools, some sort of a framework to use to think about these details as you're working on a project and you're kind of drawing up these details, or if you're a contractor, you're looking at an architect's details and figuring out how exactly to implement them in the field. But we've got a wall assembly and we're looking at, sound transmission from the, this big stack of speakers over here on the left to the person trying to read on the right. So we have our sound source and we have our different transmission paths through this wall. And for the purpose of this presentation, I'm going to just kind of break it up into two paths that I think will be helpful. So we have our structural path. So in this case, it would be drywall, stud, resilient channel, drywall. So all of the things that are like physically connected together. And then we have the cavity path, which in this case would be drywall, cavity, we've got some insulation, and then drywall on the other side. These are kind of our two sort of main transmission paths, right? And we have the sound that goes through those, and then the resulting sound that comes out the other side. And the combination of all of those cavity paths and structural paths is our transmitted path. Now you also have flanking around other places and things like that, which we'll get into a little bit in this presentation. But you could have something like an electrical outlet, right, that may not affect your structural path, but it does affect your cavity path because it puts this hole basically in there. Right now, it is still somewhat of a solid object, but it's got less weight, less mass than your drywall, and it also probably has some holes in it to allow wires to get through and things like that. So you get more transmission through that cavity path, and therefore more transmission through the wall overall. An alternative is, say you've got cabinets, and here in Portland, Oregon area where I worked as a consultant for a long time, we see a lot of apartment walls, 2x4 wood studs, RC. And when they go to mount cabinets, they'll just put in 1/2-inch plywood or OSB, sort of a shim. They'll put it in between the resilient channel or in place of the resilient channel, screw the cabinets through the drywall, through the 1/2-inch plywood and into the studs. So then you create this continuous structural path all the way across that transmits more sound, and you get more sound overall transmitted into the space. So when you think about these structural paths and these cavity paths, and maybe for an analogy to help understand this, is we can think about this in terms of like some other areas from building science. We can think about this in terms of like air barriers and thermal bridges. So a thermal bridge, right, reduces your overall insulation value. So if you've got a stud wall and you've got, say R19 insulation in the cavity, your actual insulated value of that wall is not R19 because you have these studs that interrupt that insulation layer that transmit more heat from one side of the wall to the other, right? So your cumulative insulation value is reduced by that. So you want to reduce thermal bridging, right, to improve your insulation value. So you can either do that by just reducing contact points, right, fewer studs, like wider stud spacing, or you can do that by some sort of thermal decoupling. The same sort of thing that we do in acoustics for that structural transmission path. We want to have fewer structural connection points. We want to be able to look and see, like, is there any sort of structural path in this detail where I can see rigid connections all the way through from one side to the other. And so you want to try and minimize those. And if you do have them, you want to try and isolate them acoustically. The other thing is that cavity path. And so in that cavity path, we really want to think for acoustics about sort of a continuous like mass barrier, right? And typically that's our drywall. But it may be, in a floor ceiling assembly, it may be your plywood subfloor and maybe gypsum concrete on the top, or it could be a CMU block wall or these kinds of things. But you want a continuous mass layer. And you can think about this like an air barrier, right? If you're designing an air barrier for a building envelope, you don't just go select some air barrier product that has the particular permeability or whatever it is that you want, and then just call it good, right? You have to go through all of these little details to make sure that you have continuity of that air barrier. And the idea is that you can go and you can kind of trace this pink line, right, with your pen, and you shouldn't have to lift your pen. If you have to lift your pen, then you've got a potential break in your air barrier. Same sort of thing with our mass layer in terms of these details, right? Typically it's going to be drywall, so we should be able to kind of trace that. And so anytime we have a break in that mass layer, like an electrical outlet or a gap between layers of gypsum board, we need to figure out a way to seal that so that we continue that mass layer. So I think if you're looking at these details, you can kind of use these two analogies, and I think it will help you kind of understand these complicated details, where often you're trying to also address maybe air barriers or thermal bridging, or you're also trying to address fire and all of these other sort of constructability issues. So it can get very complicated. So we'll get into some of these details now. So I've kind of broken them up into these different categories. So the first one really focused on the cavity path. And in all of these, you could find some combination of cavity and structural path. And I'm sure some of the acousticians that I see on here will be like, oh, well, Mike, there's a structural path there too that you should pay attention to. But in this case, I'm kind of focusing on the primary thing that we're trying to think of when we look at these different details. So we've got cavity path, structural path, and then one where sort of both are important, or of somewhat equal importance, we'll say. So cavity paths, get it? First, we're going to start with electrical boxes. So this is as much as possible in these where I've got details and things like that, I have tried to actually put acoustical test data to it rather than just saying this is bad, this is good, do this. Tried to actually put some data to it to show the effects. So this comes from NRC, the National Research Council of Canada report. So on the left, so here we have a bunch of different wall assemblies. So we'll kind of walk through them. So on the left, we have a base wall, wood studs, few layers of gypsum board, and some Brazilian channel. In this particular test from the NRC, we got an SEC 55 for this. If you have back-to-back electrical outlets, then you have a break, right, in that mass barrier that is your gypsum board, right? And so you increase the transmission, potential sound transmission through that cavity path because you've got all these leaks, you've got all these holes, and you've got less mass from the material of the electrical box. So you can see just these two electrical boxes in a wall, right? Just two boxes, one on each side, reduce the SDC rating by 5 points. If you think about this, like this took a wall that was comfortably above the multifamily code minimum of SDC 50, all the way down to just barely meeting code. And so if there's any other construction variation or anything else with this wall, which surely there will be, you probably now have that SDC rating down below code. So just those two little electrical boxes is a significant liability in the acoustical performance of this wall. So we need to do something to, bring this wall back to where it was. But we still obviously have to have the electrical outlets in it. People got to be able to plug stuff in. So one is, we continue that mass layer, right? So we use putty pads either on the back side or the inside of the electrical boxes. And if you do that to both of the electrical boxes, still keep them back to back, you get an SDC 55. So you bring the wall back because you've continued that mass layer. Other things you can do is just separate them further so that the sound has to travel further to get from one to the other. And especially with the insulation in the cavity, that will reduce a little bit of that sound traveling down that path. So if you have them in the same cavity but separated, you get an SDC 54, either side of a stud or like really far separated, you all kind of get an SDC 54. And an SDC change of 1 point is not noticeable. Those are essentially the same, and that's within sort of test variability. So there's a bunch of different ways that you can do this, but like carefully specifying exactly where your electrical outlets are going to go on a job seems like an awful lot of detailing, and there's just chances that things are going to get moved around. So I think just requiring this, a putty pad or something like that is a good way to do this, to put into your specifications. And also oftentimes that a fire putty pad may be required in a fire rated wall anyways. So it can do double duty. And oftentimes our acoustical separating walls are also fire separating walls, especially for, multifamily construction. Another thing on electrical boxes is, say you've got like a clips and hat channel. So your gypsum board is held out further from the wall. If you just take a standard electrical box, or switch box and mount it to your stud as is typical, then you have this gap between the drywall. So there's this even bigger gap in your sort of mass barrier. There are box extensions. They're very common. You can get these, they come in all different depths. And so you can go get a box extension that will extend that box out and then bring it flush again with your drywall layer. You want to make sure that there's a gap between the drywall and the electrical box, because that would be then create a structural bridging path, which are other type of sound transmission path we're looking at. You want to make sure there's a little gap and then seal everything, have your putty pad back there. All right, so our next detail is control joints. So in control joints, if you have a long expanse of drywall, long continuous expanse of drywall, you'll often need a control joint. Typically it's every 30 feet for walls or for ceilings. And that's just to allow for some sort of expansion and contraction. Often in the structure comes with thermal expansion and contraction, and the structure in the drywall may expand and contract at different rates. So you want to make sure that doesn't lead to cracks and buckling in your drywall. So typically you just create a break in the drywall, but then that is a break in your mass barrier. So up here are a couple sort of like standard details. These are roughly referenced to the GA file numbers that you see down at the bottom for fire. And for a 1 hour fire rating, you could really do this with just a single layer of drywall on either side. But the 2-1 wall there in the middle is what we actually acoustically tested. So in this case, you add some additional studs. You have a stud there in the middle that holds some drywall. And this is required for fire, so it's to back that gap in the drywall, which is your fire protective membrane. So it's a gap there. So you put the drywall on the stud that then provides that backing for the gap. And then you seal that with fire sealant. This is acoustic, so we also want to do it, acoustical sealant that's fire rated. Acoustical sealant stays flexible, so it doesn't like open up gaps over time as it kind of dries and cures and shrinks. And in this case, we also want to make sure that the drywall that's held against the stud is held off just a little bit from the drywall on the face of the wall, so we don't get a structural transmission path through there. See, I said they're going to always show up in both of them. And so you can do this, and this is kind of the basic gist of this. You can do this with wood studs as well. You're just continuing that mass layer, and in this case, you're kind of making it more circuitous there. All right, so those are the two that are primarily sort of cavity paths, gaps, right? And now we're going to get to structural paths, where we have a lot more of these. All right, so the first one is cabinets and other heavy static loads. So say you've got an apartment building, and you've got demising walls where you've got isolation. They're single stud walls and they've got isolation on them. Maybe it's resilient channel or it's clips and hat channel. Oftentimes you find yourself needing to mount something heavy to those walls. Now, the first thing you can do is you can just put the heavy thing on the side opposite where your sound isolation is. But oftentimes you find yourself with back-to-back heavy things. Either you've got back-to-back kitchens, so you can consolidate all of the plumbing into that one wall, or in a hotel room, you've got back-to-back sort of headboards, these kinds of things, right? So you can't just only put the heavy stuff on the non-isolated side. So if you do this, so you have your base wall here on the left, right? It's an STC 54 from this acoustical test series. We've got resilient channel, a few layers of drywall. If we do the standard detail that I saw a lot consulting again, you just put in 1/2 inch sort of plywood or OSB shims and then screw it all together. You reduce your STC rating by 8 points. You go from a 54 to a 46. So you go from comfortably above multifamily code minimum to well below that code minimum. And so now you've got a wall where you don't meet code and you're very likely to get complaints, especially because kitchens tend to be noisier places. You've also got people, moving pots around and things like that, slamming cabinet doors, shuffling plates in there, all of these kinds of things, right? There's a lot of noise sources that are all there very close to that wall. So you need to maintain that isolation of the structural path. So the way you can do that is use an acoustically isolated backer. So there's two things here. So sometimes I have seen people suggest just mounting the cabinets, say, to the resilient channel. But resilient channel is made out of 25 gauge 18 mil steel, which has very low screw pullouts, and it's intended to be flexible. It's not really intended to carry a heavy load like a cabinet or something like that. So I'm never comfortable with that from a structural load capacity standpoint. So you really need something that maintains your acoustic isolation, but also provides that structural support and a large mounting area for your cabinets. So you want to look at providing some sort of isolated, acoustically isolated backer there. Similar sort of thing happens if you have clips and hat channel. You need an acoustically isolated backer there, and you need one that just matches that depth of the clips and hat channel. So just want to make sure that you're continuing that isolation, that you don't have any sort of rigid connection points through there again. Similar sort of thing for grab bars and handrails. Say maybe you're doing a retirement home or assisted living facility or a hospital or something like that, and you've got sound isolation between your corridors and your units, but you've got a handrail along there, or you've got ADA compliant bathrooms that have grab bars in them, right? And some of those grab bars happen to be on a demising wall where you need acoustical isolation. So same sort of thing, right? You use an acoustically isolated backer. So you need to maintain your acoustical isolation. So you need to have some sort of resilient element in there. But then also you need to make sure that you have the structural capacities to support the grab bars and handrails and meet the load requirements for them, which typically the load requirement for handrails is a 200-pound load in any direction. And for grab bars, it's a 250-pound load in any direction. So if you're looking at some isolation, you need to keep those load requirements in mind as well. So similar sort of thing, again, for clips and the isolated backer. And here there are acoustical tests for these backers. That's the other thing, is you want to make sure that you've got documentation of these other things that you're doing for details. Make sure that there's some documentation and testing to show that they can maintain that acoustical performance. And in this case, with the isolated backer, it was an STC 53. Instead of an STC 54, again, a 1-point change is negligible. All right, next bit here is a deflection head. And for those of you that are paying attention, you'll notice that the image that I pulled here doesn't actually have a deflection head in it, but I just found something that had steel studs that looked kind of cool. So forgive my non-applicable image. So a deflection head, you find this a lot in like concrete construction, where you may have some deflection movement in the structure for one reason or another, and you need to allow differential movement between a stud wall and the structure up above. So the deflection head itself does reduce the sort of structural coupling, that transmission path from the concrete structure up above to the studs down below. And really what we're trying to do is, say there's some impact sound on this concrete slab. We want to reduce the amount of that sound that gets down actually into the studs and then radiates out into the spaces beside. So the deflection head does create some amount of decoupling between that concrete slab because it's kind of a slip joint, right? But if we want even more sound isolation, say we've got some, very critical space, these are very high-end, luxury penthouses in some fancy New York tower, or we've got a recording studio or something like that, where we want to use the belt and suspenders approach for things. We can isolate that top track with an acoustical isolator. And if this is a non-fire rated wall, you'll typically just put fiberglass in that little gap that's created by the isolator. If it's fire rated, then you typically pack it with mineral wool. And then if you've got isolation on one side of this wall, here we've got clips and hat channel, that increases the thickness of the wall. And so there are some special deflection tracks that have this little kind of bulb that you see there that sticks out on the left, that bumps that gypsum board out so that it lines up with the gypsum board on the primary wall. So a lot of little details here to kind of pay attention to. You'll also notice that, so you have these two pieces of gypsum board up above that kind of overlap the other gypsum board. So that means we have, because we need to allow these to move up and down. So you want enough overlap where you have, again, this continuous mass layer, so you don't have any gaps or anything like that. Because here you can't necessarily seal that because it has to have this differential movement. So you have enough overlap to kind of minimize that crack. You want to make sure you've got lots of insulation in there, so any little bit of sound that does leak through, you've kind of attenuated that cavity path as much as possible. And then the drywall, these upper strips, only gets attached to the upper deflection track so that then it can move up and down. So a lot of little details in here. And then typically these kinds of things, you've got some sort of lower ceiling or something that covers up all this kind of funky, not so pretty looking stuff where you've got your deflection head. There are non-rated versions of this. That's much easier to do non-fire rated, but there are also some fire rated versions. There are some UL designs, some UL fire rated dynamic head of wall designs that also include acoustic isolation. So you can kind of put all of those pieces together. Just you got to do some digging to find the right ones. Furred walls. So furred walls could be you want to fur a wall out from a CMU block wall or maybe from an existing wood stud wall. So the CMU block wall, again, maybe you've got something like a recording studio where you're going for very high levels of sound isolation. So you've got the CMU block wall for a lot of mass, but you want to still further improve the acoustic isolation and also provide space to, run electrical lines, different cables, services, and things like that. Could also be maybe that the CMU block wall is a bearing wall for some concrete slab, and maybe there's an emergency generator or something, or some mechanical penthouse up above, and you want to make sure that any sound that gets into that structure, into the CMU wall, isn't radiated out into the space below. So you have this isolated furring wall. So you'll kind of build a typical stud wall, and you could just separate the stud wall from your CMU block wall or your wood stud wall, and just use that separation, that gap, as your isolation. That works totally fine. But that means that then your stud wall has to, have that height, have the span on its own, have the structural capacity, which may mean wider studs, more studs, thicker studs, heavier gauge studs, those kinds of things. So oftentimes those furring walls will get braced back to the primary sort of structural wall. But again, that creates a structural connection and creates more sound transmission through. So you can use an isolated bracket, just a little L bracket with a rubber isolator on it, for instance, to isolate that connection. So you still get that structural tie back, but you don't get that acoustical transmission from one side to the other. The wall on the right, this might be common. Say you've got a, sort of a strip mall situation, right, where you've got a bunch of separate tenants. And you've got one tenant that's, a restaurant or something like that, a noisier space, and then next to it you're going to have, an accountant's office. And they don't want to be bothered by the restaurant noise. They also want some speech privacy. People are discussing financial information. They don't want that to be heard on the other side. But you've got an existing wall there that may be, load bearing, carrying some of the roof structure. It's also probably a fire rated wall, so you really often can't touch that wall. So then you can kind of fur out this other wall. And again, by kind of tying back to the structure with these isolated brackets, you can maintain that acoustic isolation, but make it easier to construct your wall structurally. All right, shear walls. Shear walls are kind of like where we've got isolation on one side of a wall and we want to mount something heavy. If you're only trying to mount something heavy on one side, you can put the isolation on the other side. Shear walls are similar. If you only need a shear panel on one side of the wall, you can try and put your isolation on the non-shear side, and then that can work just fine. But double-sided shear walls are where it becomes really problematic because shear's on both sides, and that makes your isolation a lot less effective. So you can see here again a series of tests. We start with just a basic 2x4 wood stud wall, shear panels applied to both sides. STC 36, nowhere near code. As we add some drywall, the performance gets better. And then the wall there in the middle, we add some isolation. So we got clips and hat channel. And that does bump up our STC rating. But we've created this little bitty air cavity between the plywood and the drywall. And that air cavity allows some sound to build up. It's this little reverberant space, right? You've got these two hard surfaces that are constraining the sound in that space. So you'll get sound that kind of builds up in there, and then you get more sound transmission because of that. Essentially, that's how it works. So if we put some insulation into that space, the insulation doesn't actually block the sound going from one side to the other, but it reduces the buildup of sound within that cavity, so there's less energy to kind of go from one side to the other. So you can see adding the insulation gives us this big boost. So again, this one kind of structural path and cavity path. So we use the isolators to isolate that structural transmission path, but here we need the insulation to reduce the transmission through that cavity path. And we need a big enough gap, a big enough airspace between that shear layer and our drywall, so we can, one, put insulation in the cavity, we just have room for it, And it lowers the mass air mass resonance. It just makes the acoustic isolation more effective, we'll say. And so you can see there on the far right, this is a different test series. This is a 2x6 wood stud wall, but this just had resilient channel and drywall over the shear layer with no insulation in the air cavity. And you can see that's not a well-performing wall. So just adding resilient channel is not effective enough to isolate that structural transmission path. All right, now we'll get into the cavity and structural paths. And I see some good comments and questions in here. I'll come back and touch on some of these, and I can kind of go back to the questions as we go. I want to make sure I have enough time to get through all of this. So I'll come back and address those questions and comments at the end, hopefully. All right, so first one is door and window jams. So you might run into these. There are some projects that I worked on as a consultant. There were apartment projects that overlooked, I-5 or I-405, the interstate highways here in Portland. And so, on those, oftentimes your windows are your weak point acoustically. It's hard to get really high SDC rated windows, doors. Certainly it can be done. They tend to be a lot more expensive. And so for these where we had apartments that were overlooking a highway or something like that, we tried to minimize the size of the windows, which I know for daylighting and all of these other reasons is not ideal, but so is hearing a highway all the time. So we try and find that balance. And then we would also try to upgrade the wall, because if you just have a basic wall with some metal or hardy board siding and some plywood on the outside and drywall on the inside, that's maybe an SDC 36 or 40 or something like that, which is not far off from what the window is. So we want to try and minimize the amount of sound that's coming through the wall, so then we're really just kind of dealing with the window. So sometimes we would use resilient channel or clips and hat channel on those walls, and we would have to deal with the detail of this window inside of it. Could also be you're designing a skiff and you've got a door in that, and you've got isolation on your walls, or a recording studio, these kinds of things, right? So how do you handle this detail where you have clips and hatch channel that offset your drywall further from your studs? And so when you run into a door jam, it creates this little gap there. And how do you handle that detail? So here on the left, you can see the header. And so we have the clips that are running parallel, clips and hat channel that are running parallel to that header. And so you have your drywall come down, and then you have a little return that's supported by some L angle. And that return there is to block that little open cavity path that would be there otherwise, right, in the gap between the drywall and the header. And then your door frame is mounted to the header, but held off of that drywall, again, so you don't get this continuous path that ties the drywall to the structure. Now, of course, your door frame is a continuous path across, and your door is also possibly a weak point. But if this is a recording studio or a skiff, you probably have an SDC rated door that's probably in a similar ballpark of performance as your wall. Or if this is an apartment or a hotel or something like that, your door is probably not an acoustically rated door, but you're still going to have this isolation on the wall, because maybe just near this you've got another wall, and then there's a bedroom where you do want that isolation from the corridor, for instance. So you're still going to just continue your isolation, and you still need to address this detail appropriately. Similar sort of thing here on the right. This is for the jam. Same sort of thing. We have this little return. We have our L metal that just runs down and ties all of the different hat channels together. Very similar sort of situation for a window. But for a window, you often don't have like a window frame that sort of caps the end of your wall or something like that, or caps your header, and you'll have a gypsum board return or something like that that goes in there. So here on the left at the head, you can see this bigger L metal and a bigger gypsum board return. So again, we're continuing that mass layer, but we're holding the gypsum board off of the structure. We're sealing it with acoustical sealant, fire rated sealant if and when necessary. So that we continue that mass layer, we seal everything up, but we maintain the acoustic separation so we don't create some sort of structural path for things to be transmitted through. Similar sort of situation on the jamb. When we get to the windowsill, it's a bit different. For the door, we don't really have the sill. That's a different thing. It's at the floor. Maybe we'll talk about that in the floor ceiling assemblies bit. But at a windowsill, we're gonna have the sill. We can't necessarily float that because somebody might put some plants on it. Your cat might jump up on it. You might sit and lean on it. Your kids might climb on it or something like that. So if you try to float the gypsum board, it's just gonna crack and fall apart. So you got to have some sort of rigid support for that. So in order to accommodate the offset of the drywall, this gap created by the clips and hat channel, you put some blocking there to support your sill so it's not just cantilevered out, and then you kind of run your drywall up to it. And the drywall that's isolated on the clips, you want to allow it to continue to move freely, so you keep it separated from the blocking and from the sill. There's a lot of this, all of these details. There's going to be a ton of different ways to do this, right? Architects are going to detail windows and doors differently, windows especially, all kinds of different ways, right? And so these are just ideas, things to think about. And again, when you're looking through these details for your particular project, think about that cavity path and that structural path. Like, do we have a continuous mass layer? And also, is that sort of continuous mass layer acoustically separated from the other side of the wall, partition, whatever it is? And if you can kind of really think about those two things, think about like thermal bridging and air barriers, that can help you look through these details and find potential weak points in them. All right, so intersections. I think we're doing all right on time here. So first intersection we'll talk about is a wall-to-wall intersection. And these can be tricky because often you're dealing with acoustics and fire. And fire tends to like things all buttoned up and touching. There's some clear exceptions to that, but and acoustics, we typically want to have things separated, but we still want them all sealed up. So on the left, we have a non-rated partition. This could be like a wall between bedrooms in an apartment, something like that, that runs into a rated partition. And in this case, the non-rated is non-rated for acoustics and fire, and the rated would be rated for fire and acoustics. In wood frame construction, you can use a wood stud as fire blocking. So it can interrupt the fire protective membrane, gypsum board. So you can sort of start and stop your gypsum board at this intersection, right? You start and stop it, and then you have this. And if you look at this, let's see, I don't know if you can see mine. Do I get a little pointer thing over here? If you look here and we look at like tracing structural paths, the way I've actually drawn this, you have this, and there is this continuous path here, right? So not entirely ideal. Perhaps you could hold this stud off, but again, having a continuous sort of fire protective membrane through here takes precedent over the acoustics. So this becomes a really difficult one to do, for fire and acoustics. But you do have this sort of circuitous path, and there is a bit of loss as the sound transfers through all of these studs and things like that. And I think actually the National Research Council of Canada has done some testing on these kinds of different junctions and these things. So that's a good resource, especially for any of you acousticians. If you haven't seen their flanking documents for lightweight wood frame construction, it's worth checking out. Over here, we have the same sort of thing, except we have resilient channel on this side. And I did see somebody say, hey, could we put the resilient channel on the corridor side? You can totally do that. But then if you have a handrail, for instance, on the corridor side, because maybe this is an assisted living facility, then you need to use those acoustically isolated backers for the handrails. Or oftentimes, if, especially here in the Northwest, we're in a big seismic zone, you'll have shear panels on the corridor side, because oftentimes you'll have kitchens and bathrooms on this side, and having the shear panel there makes it really hard to run all those services in your wall. So they'll often put the shear panel on the other side, and then, as we've shown before, putting the resilient channel over the shear panel doesn't work. So there's a lot of different details to deal with in these. And again, you got to just kind of think through all of those, figure out what's the best solution for your particular situation. For steel, it's a little different because for steel, we can't use a steel stud as sort of fire blocking to interrupt that fire protective membrane. So if we have a non-rated wall intersecting a rated wall, acoustically on fire, the rated wall is going to run continuous across this non-rated wall. Now you do have this continuous gypsum board layer here, which is a continuous sound transmission path. So you could get flanking through here this way. If this is a wall between bedrooms, maybe it doesn't really matter. But if this is also maybe an acoustically rated wall, but non-fire rated wall, say this is an office tenant on this side and a different office tenant on this side. So there's a fire rated wall between them, but you also want acoustic separation between these two offices. Then this is a potential weak path here. And perhaps you could sort of put basically a control joint, a little gap in this, seal this as it's inside of this wall. That's a detail though to check with your local AHJ to see if you can do that for fire. If both walls are fire rated and they have the same fire rating, so both 1 hour rated for instance, then one wall can bisect the other wall. And you can see here, we've held this stud off, we've held the drywall off, we've held the drywall off here. So there are no, you can't find, you can't come in here and trace a path where it's all rigidly connected, right? But we also still have a continuous mass layer everywhere. So you're at least going through 2 layers of drywall any way you go through this. Wall to ceiling. Again, in wood frame construction, we can use a double top plate here. We can use the wood 2x4s as fire blocking, and we can break this fire protective membrane, whether we're non-acoustically isolated or acoustically isolated. You're going to need to add some blocking here because you don't want to tie this wall into whatever your acoustic isolation is. Acoustic isolation is meant to allow movement. You don't want this wall moving. So you want to kind of keep those things separate. Steel frame construction, I don't have in here because it's a lot trickier. Where you've got like a steel stud wall, the steel joists. That also tends to be a lot less common. More commonly, you have steel studs to a concrete slab or concrete on like a metal deck or something like that. So here again, we may want to reduce the amount of sound transmission from the space above down to this. And so we can have some acoustic isolation. We have seals here, and also we've got this gap here, so we put some insulation in that as well to kind of protect this cavity path through here. Wall to floor. Another place where, again, we want to make sure that we're sealing everything well, but we're also not creating any sort of structural transmission issues. So our preference on the drywall side is to pour your gypsum concrete topping first and then run your drywall down to that. There was a project many years ago that PAC was involved in, it was long before I was here, where a wall was installed and then they poured drywall. Well, the junction between the gypsum board and the subfloor was not sealed well, and then they had issues. We got called out. And when we went out, we asked them to remove the drywall so that we could inspect the wall behind it, see what if there are any installation issues or anything like that. They went to remove the drywall, but they couldn't. Turns out it was embedded in the gypsum concrete. The gypsum concrete had flowed around and encapsulated the bottom of the drywall. So then you had this sort of rigid connection path through. So we want to make sure that we don't do that, that your drywall is sort of decoupled, isolated from your gypsum concrete. Also, your gypsum concrete is typically also decoupled from your structure. So you want this sort of bathtub isolating that, and then you want to make sure that your drywall kind of floats separately, so it can freely float on your clips or your resilient channel or whatever it may be, right? A wall to floor. Maybe we've got something very noisy down below and we don't want that sound getting into our concrete slab and up into the structure. So we can isolate the bottom track with a rubber isolator, for instance, and a fiberglass pad in here. You also want to make sure that you isolate not just the steel track itself, but the fasteners, right? So you'll have some sort of isolated, a rubber bushing or something like that to isolate your fastener. And then you want to seal here again at these bottom joints to maintain that mass layer. All right, window mullions, and I think that this is our last one here. So window mullions are another really tricky detail. One, because they're all different. You've got all these different sizes and different constructions of window mullions, right? Also, like you can see it from the outside, so anything that you put there is going to be visible. So there's an aesthetic aspect to it. Also, oftentimes the wall is a fire rated wall, and so how do you deal with fire ratings here? There's a bunch of different stuff that comes into this. So here we have a potential cavity path, right? This gap, often there's some sort of little gap left between the wall and the window mullion. And then you also have a structural path, right? So, you know, here we've got this wall that's got 2 layers of drywall on either side. So there's a lot of mass in this wall. But here, maybe it's just a hollow aluminum mullion. So there's a lot less mass. So you get a lot more sound transmission through this structural path. Also, the glazing itself may be a structural transmission path. Even if there is a bit of a break in here, you can get some sound transmission this way too. So one way to do that is to add isolated mass. Same thing we're doing when we're adding, you know, drywall on resilient channel or isolation clips or something like that, right? So, but that mass needs to look good. So you have some sort of custom aluminum section, some mass loaded vinyl in it to add your mass. Then you have an acoustic isolator. They can either be screwed into your mullion. Usually people balk at that. It can also be attached with a dress washer and some like VHB tape. And then you have this here. And this, when tested, this was a wall that had a section that was cut out of it. This was built into it. The wall was an STC 64 with this, and it was an STC 58. And I think in this particular instance, it was a very small opening. I think it was actually like a door opening, and the mullion was like 6 inches. So it was a pretty significant portion of the overall surface area of the wall. So you can do that. There's other different mullion caps and things like that, right? Again, you want to make sure that ideally things have acoustical testing, either a lab test or some sort of, you know, you do some mock-ups and you do a field test to see how all of these details work out. Another simpler option is there are just kind of foam seals that you can put in here. You know, they're not going to necessarily match the same aesthetic as your aluminum window mullion, but they can be easier to install. And again, they seal this, so you're sort of sealing that cavity path. And they're also adding some mass and extra thickness to this to help kind of reduce that structural path. And again, here you can see these not tested in a window condition necessarily, but tested in a gap in a wall. And they were able to keep the STC rating of the wall fairly close to the base wall rating. All right, I think we're right on time, and that is it for all of my bits. So I will bring Steve back on, and Steve got some questions for me.
Yeah, Mike, we got some good questions here in the Q&A. I'll start from the first question we got from Kimberly. And she asks, is there an online design manual or STC details for existing partition assemblies, sort of like there is for UL assemblies?
Great question. Not yet. So, well, I guess I should say that. I think some of the drywall manufacturers and some others have, you know, like USG, for instance, I know has had some, you know, design details. They have a lot for fire. They also have some that kind of address acoustics and things like that. But we are in the process of putting together our own database for PAC that will have CAD versions of these that you can get as a PDF or that you can get as you know, hopefully a Revit model of some sort, 2D. Maybe we'll have some 3D Revit models in there as well. We have a full-time CAD designer now who does a lot of our like spring shop drawings, but is also helping with a lot of details. So my goal this year is to put together an online sort of searchable, filterable database of these different these details. And as we keep adding more, as more come up for projects, we'll try and draw those up and put them in there. So stay tuned for that.
Thank you, Mike. Next question comes from Christopher Lamb. And his question was, how critical is the actual quality of the installation of of the putty pads to achieving the full STC on electrical boxes and such?
That's a great question. And I don't, I don't have any data for it that I can think of, any tests. I would say that there's going to be some obvious things, right? Like if somebody just slaps the putty pad on there, but it doesn't actually like come back and like make contact with the drywall, there's obviously like big gaps, then you're not going to get the full effect of that putty pad, right? You want to make sure that you cover up all the gaps and stuff like that. So I would say that it's somewhat scary, and that like if there's no gaps, it's good. If there are any gaps, it's bad. But the more gaps, the worse it's going to be, and those kinds of things. And I guess you could, spread it out, get it really thin where it's not really adding enough mass and things like that. But again, think about an air barrier for that kind of a thing, right? Like if all your gaps are sealed, right, and you can't see any places where like air is going to get through, then you've probably sealed it sufficiently for sound too.
All right, thank you, Mike. Next question Don posed when you were reviewing cabinet application on stud walls, or direct cabinet application. And his question was, does the cabinet provide any sound control itself?
I mean, maybe, depends on the cabinet. And also, like, usually the cabinets don't cover the entire wall. There's parts of the walls that don't have cabinets on them, so you're still going to get the same amount of sound transmission through that wall. In some of our tests where we've added a cabinet to a wall and we've had the cabinets isolated, I think maybe in one or two instances we've seen putting the cabinet on there, especially like weighting the cabinet, did maybe improve the STC rating by like a point, but it wasn't much. And in some of the tests we did, I think maybe it was like an 8x10 wall or something like that, and we had a full row of upper cabinets and a full row of lower cabinets, so most of the wall was covered by cabinets, and it didn't really increase the STC rating by more than a point, if my recollection serves me. So I would not count on the cabinets to improve your STC rating or your sound isolation. But if the cabinets and their backing are not acoustically isolated, I would definitely count on them to degrade your acoustical performance.
Thanks, Mike. Lance, this was in regards to stud walls. Does staggering studs help?
Yes, so staggering your studs. So for anybody who's not familiar with it, like say we're doing wood frame construction, you would use like a 2x6 top and bottom plate, and then you would use 2x4 studs staggered on that. So you'd have, a stud on this side and a stud on this side, so that the drywall is only ever attached to one side of the studs. So you have this more sort of circuitous path. You still have a continuous structural path, but it's like drywall, stud, bottom plate, stud, drywall. So that will provide better sound isolation from one side to the other. It's not as good as the non-AIA part of this, so it's not as good as like the Rizik clip and hat channel, and it's also not as good as like a true double stud wall where you have two totally separate top and bottom plates. But it takes up less space, bit less material maybe, and yeah, you can just mount all kinds of crap to either side of it. But I would just kind of look at that trade-off of the isolation levels that you get. Maybe for a staggered stud, you need an extra layer of drywall to match what you would get with clips and hat channel. So kind of look at the total assemblies and then kind of run your cost comparison and constructability comparison between them.
Thanks, Mike. All right, next question comes from Joe Morris, and this is in regards to acoustical caulking and how do we seal gaps between the top wall and corrugated metal or concrete deck?
I see also a comment from Neil Shaw that looks like maybe it was, I don't know what that was. I've seen Neil Shaw has had a few comments in here, and those are always usually good from Neil. So sealing gaps between the top wall on a corrugated metal or concrete deck. So if it's a fire rated wall, first I would go look at fire rated details for that. So there's a lot of like UL head of wall details that address this. Sometimes you can sort of castellate your gypsum board where you cut it to follow that profile. It's a nightmare for the contractors, but I mean, you've got to have this continuous fire protective membrane. Also, sometimes they'll put like they'll stuff the upper bit of your metal deck. They'll stuff that with like mineral wool. and then put like a steel plate over that, and then you can tie your wall into that. It also depends on if your wall is running perpendicular to those bits or if it's running parallel. Okay, Neil's staggered studs. So yeah, and the flutes. Thank you. Somebody says flutes. Yes, it's the flutes. That's the bit. So you can pack the flutes with mineral wool, and then you can have a steel bit. There's some details, like I said, in UL. I think probably some of the drywall manufacturers also have details for this. This will be one I have to add this, I guess, when I go to floor ceiling details. This is a good one to put on my list. But again, really just look at from the acoustical standpoint, like, do you have a continuous mass layer, right, on either side, right? Is it sealed all the way? How are you sealing it? And then are you sort of maintaining your acoustic decoupling from either side? And are you creating any sort of structural bridges with how you do this detail? But those are always tricky.
Thanks, Mike. Just to read Neil's comment in regards to staggered studs, he made the comment that in some jurisdictions, staggered studs are not allowed without structural stiffening. I believe that's what you're saying. So I haven't heard that, but it's a good comment.
Yeah, I mean, so like one thing, and I don't know if Neil's talking like wood studs or steel studs, but like for steel studs, like I've seen some. Yeah, Neil. In a minute, I'll run through some questions, and then I've got a little bit of extra time. And Neil, I would love to unmute you and have you just jump into the conversation in a minute, and get your input on this. But like for steel studs, if you just look at the standard like span tables for steel studs, it assumes that the flanges, the sides of the studs are attached to drywall to fully brace those flanges, because if the stud twists at all, then it gets out of its strength axis and it can couple. It's like if you take a soda can and you just twist it a little bit, then it's way easier to crush than if you just try to push straight down on it. If you don't have both of those stud flanges constrained with like drywall directly attached, then your spans go down, and then you have to brace them internally and things like that. So there's other sort of structural things for fire and all this kind of stuff to pay attention to. So yeah, once you get into the details, the devil's in the details, and it can get really complicated to try and maintain structure, fire, acoustics, and all of these other things.
All right, thanks, Mike. Joe also asked the question, will these slides be available? Yes, we will have a copy of this presentation that will be posted to our website, and we should also be able to generate a link that we can share to everybody who attended today. Next question comes from Lance. Define what makes acoustical sealant.
Oh goodness, there's an ASTM standard. I want to say it's C638, but I could be wrong about that. But really the primary defining thing for an acoustical sealant is that it is non-hardening, that it maintains its resiliency. So over time, it allows the two things that you're sealing to kind of, it's not ASTM E90. E90 is the STC test standard. But it allows the two things to move slightly and allows the sealant to kind of stretch and shrink. So that gaps don't open up over time. So it's that resiliency. So I know that there are a number of acoustical consultants out there that have a piece of drywall in their office that have a bunch of different, acoustical sealants on it that they've just put little lines of it, and they just have it sitting there in their office. And then every once in a while, somebody will go over and poke it and be like, all right, is it still squishy? C919, that sounds right. Somebody can look that up and confirm, but I think C919. So there is an ASTM standard for like acoustical sealants and things like that.
Yep, that is correct, Mike. C919 okay. Standard standard practice for use of sealants in acoustical assemblies. Mm-hmm.
There we go.
All right, next question. Thank you, Lance. Good one. Jamie Lemon asks, can you touch upon the use of acoustical sealant and whether any sealant can be painted over if it doesn't match the room's wall color?
So whether or not you can paint it and that kind of stuff, putting a layer of paint over it acoustically, I can't imagine a situation where that would do anything acoustically. But really the painting the sealant comes down to chemical compatibility between the sealant itself and the paint, and that's going to be a question for the manufacturer of the sealant.
All right.
But as far as I know, in my time, I can't recall any situations where a contractor came back and yelled at me about painting acoustical sealant. So not that common of an issue, at least I would say.
All right, thanks, Mike. Hannah had a question about slides being available, and I think I answered that one. Yes, they will be. Next question comes from Jerome Steckling. Where can wall assembly isolation ratings be found below 125 hertz to 20 hertz?
All right, so I'll give the short answer first, and then maybe we can get into the long answer in a little bit, and maybe we'll get into the long answer when I bring Neil on. So the short answer is for acousticians especially that tends to dig into the full test reports and the frequency data, the like 1/3 octave band test data for our wall and our floor ceiling tests. We have an online database of our acoustical tests. So you can go click this button to register if you haven't already, or to log in. Our login is running very slow now, so if you go there, please just be patient. It takes about 20-25 seconds to load sometimes, but eventually the login and registration page should load. Once you're registered, you can come over here to PAC assembly selectors. So this one, the engineer version, has access to full test reports. And if you come here, we'll just pick some random wall. Got a test report. In this test report, of course, I pick one that I don't have in there. Let's just do this. I know these. So, older test reports tended to not go down as low in frequency. Newer test reports like ours from North Orbit, here on the main page, it will go down to 50 hertz. And in some instances, they provide additional data that goes down even lower. We tend to not go down all the way to 20 hertz because just our ability to measure precisely down at such low frequencies is very, very limited. And so that data is really of limited use. I know oftentimes we're trying to isolate down to that because we've got big high-powered sound systems with subwoofers and stuff like that. But measuring down at those really low frequencies is a limitation of our current test standards, which I would be happy to have a very long conversation with you about some other time. And Steve, while you queue up next one,
Right,
I'm going to
thanks,
see is Neil Shaw. I am allowing your mic if you are still here, so you can hop on if you would like to. Yeah, what's next, Steve?
Okay, next question is, 1 second here, just responding to a chat. All right, the next question comes from Maria Castellucci. Stud gauge for metal studs makes a difference in the STC values. What gauge studs were used in the testing examples given in your steel stud test that you've shown in the presentation?
Which steel stud tests?
So some of your details with steel, yeah.
There's a number of different ones. So again, if you come into our assembly selector here, so there's some that have like this backer here. So this is one that I referenced with the acoustically isolated backer. So this is RISC 1 clips and the RISC 1 backer. These are 20 gauge 33 mil, so a structural 20 gauge steel stud spaced at 16 inches on center. And if you want to do a deep dive into stud gauge and things like that, you can come to our main page and we have our steel stud brochure, where we have a whole bunch of test data for steel studs with various gauge and spacing, different isolation options, all these kinds of things. There's also a bunch of that kind of information included here in our assembly selector. I think I also showed one for the control joint, and that one, I don't remember the stud gauge on that one. Let me see if I can find that one. Go fast. Must have been 1, 2. That would have been 20 gauge 30 mil, so a non-structural 20 gauge steel studs at 24 inches on center.
All right.
Hey, Mike, I'm here.
Hey, Neil, how you doing?
I'm doing great, great. Thank you. First, I want to say, I always learn something new from your webinars, and you remind me of stuff I've forgotten.
well, I appreciate that, Neil, especially coming from you. If I can teach you something
Okay.
new, I feel like I'm doing all right.
Okay. And there are just three comments, if I may. One,
Sure.
when you talk about a sound-rated door, I prefer to say sound-rated assembly because
Fair point.
people buy doors that have a sound rating, but you need the frame, the seals, the hardware, the threshold to get what you're paying for. Okay.
This is very true. That is a great point. I mean, doors were, not the primary emphasis of this, but that is entirely true. And same thing for a window. Like I have seen for some windows, you'll just get testing for the glazing itself, and it doesn't include the frame or any of those kinds of things. So
Right.
that's a very important point for people to pay attention to.
Right. I have clients who say, "Well, I went to the Virocon glass website, and they said that this glazing gives me that." I say, "Yeah, but you have to put it in the frame." Okay.
Yep.
The next thing is when you mentioned you have to fill that small air gap when you're furring stuff out. And the problem is some people have a half-inch gap, but they try and put 1 inch of fiberglass in there. And by compressing the fiberglass, you're creating another structural path. Okay.
This is true, and this is actually I have another phone call here in about 20 minutes where we're talking about that exact question. I think for a floor ceiling assembly, and if you look through some of our testing, you will notice that in places where we have very small plenum spaces, such as our shear wall test, and we're running another set of shear wall tests on Monday at North Orbit Labs. We will often put 2.5-inch fiberglass insulation in the cavity created by the rivet clip in the hat channel, which is 1 inch and 5/8. And that does compress the fiberglass a bit, but the fiberglass is such low density because we're just using standard, like, I guess this would be R8 bat, but it's very low density. It's, 0.5 pound or thereabouts per cubic foot. So you're not compressing it enough to where it starts creating some structural coupling, as far as I can tell. But there is, of course, a point where you compress the fiberglass insulation enough where it will create a structural transmission path from one side to the other. And if you try to use mineral wool, which I know a lot of people will kind of like, commonly it's thought that mineral wool, is better acoustically than fiberglass. I take issue with that, but it is a much higher density and it's much stiffer, and so you can't compress it nearly as much before you start getting some, acoustic transmission from side to side. So yeah, that's another good point.
Yeah. The point is we have no idea sometimes whether it's mineral wool or fiberglass and how much they could compress it. So I always try and show my details a little bit of air with most of the cavity filled with the fiberglass. Okay.
Mm-hmm.
Okay. And the last point was regarding the staggered studs. We had a large post facility in Burbank where between the edit rooms we used staggered studs because we were short on, let's say, space.
Okay.
And so when the inspector came in, he made us tie them all together in three heights, which basically broke our isolation and created a nice structural path. So before it's like nitroglycerin, some of the stuff we do. Know what you're doing before you do it, and we were kind of blindsided by that inspector. But thanks again for this great webinar, Mike.
Yeah, thank you so much, Neil. It was interesting. I was just looking because we're doing these shear wall tests, and the lab was asking me like what screw pattern to use to attach the shear panels to the studs, and so I was going through and I was looking at some like Woodworks documents for guidance on screw spacing, these kinds of things, because there's a whole bunch of variation in that, and I wanted to make sure that what we were actually testing was kind of applicable to the real world. And in one of those, I found this one that was on shear, and it had a picture of a staggered stud. Let's see if I can find it and throw it in the chat. It had a picture of a staggered stud wall. Yeah, here it is. It's a tiny little thing. I'll copy it and throw it in the chat here. But it's a staggered stud wall, and it's braced across, and all the studs are tied together. I imagine this is exactly what you're talking about, Neil, from your project.
Right, right.
And yeah, that just, the point is that they're separated. There's not this continuous structural path. So again, like if you're looking at your drawings, say like, can you trace a line that's got this continuous structural path all the way across? And if you can, that's an issue, and you need to try and figure out something different usually. All right. Any
All right, we have a
other
few more
questions come
questions,
up?
Mike. Yep. Lance asked, will you be doing a seminar on room slash spatial acoustic design?
I will not. Here at PAC, our focus is just sound isolation. We don't do room acoustics. And while I was a consultant for 10 years and I did some room acoustic stuff, that is not my area of expertise. And there are other folks that are much better qualified to talk to you about that. If you have some questions about room acoustics for a project that maybe also involves sound isolation, I'm happy to give you little pointers and point you in the right direction. Some acoustical consultants you could talk to, some other companies that have those kinds of products and have some in-house acoustics expertise. But yeah, that's outside of my purview at PAC.
All right, thank you, Mike. Next question comes from Mike Valensic, and he's asking, can you speak to mineral wool versus fiberglass insulation?
Yeah, sure. So first off, I guess I would say if we're gonna compare mineral wool and fiberglass, we want to be specific about where we're comparing them and in what context and all these kinds of things, right? And so in the context of fire, there are some significant differences between mineral wool and fiberglass. There are different uses for those within fire-rated designs. They have different requirements. They can do different things. So in that case, there are some very clear distinctions between them in terms of how they're used. In acoustics, I often see people using, specifying, recommending, and this often comes from sort of like internet forums and things like this. I see this a lot less from the professional acoustical consulting community. But I will see that mineral wool is often thought of as providing better acoustical performance. Typically, like if you put it in the stud cavity of a wall, using mineral wool instead of fiberglass will give you higher levels of sound isolation from one side of the wall to the other. In the testing that I have seen, I have not seen that. There might be some small differences. It might be that the SDC rating for the wall with mineral wool is, a point higher than the wall with fiberglass. But typically the difference that I see are within the realm of the test variability. So if you just run the test again, you can get about a 1 point. You would expect, about a 1 point range in your SDC ratings. So if you have a mineral wool wall that's an SDC 54 and a fiberglass wall that's otherwise identical that's an SDC 53, you can't say that those are different. Even if they're tested at the same lab, statistically, that's not a statistically significant difference in their SDC ratings. Now, if you go and you dig into like the third octave band transmission loss data, like maybe you'll see some bigger differences there that maybe are statistically significant, but so I generally, my approach is that the often additional cost of mineral wool is not warranted for acoustics alone. There may be some reasons for fire or other things where it is warranted, but that's my general take. And there may be some exceptions. I'm sure Neil Shaw or some of the others on here could probably come and chime in with some exceptions.
All right, thank you, Mike. Looks like that's the end of our Q&A questions. People do have some questions about when part 2 would be available for presentation. We will be sending out announcements several weeks before that, before we have part 2 ready to go. So just stay tuned.
Yeah, thank you, everybody. Really appreciate it. We see a lot of folks have stuck around well past the hour, so I really appreciate that. I will see you in New Orleans, Neil. Yes. So yeah, anybody that's going to be at the ASA conference here in New Orleans coming up next month, I will be there. Anybody that's going to be at NoiseCon in June, I will be there. Anybody that's going to be at NCAC in July, I'll be there. So come stop by, say hi. And yeah, thanks again, everybody. And sounds like I need to get cranking on part 2. So if you got any floor ceiling assembly details you would like addressed, shoot us an email, give us a phone call, and we'll see what we can do.
All right, thank you, Mike. If you need to get in touch with us, go to PACinternationalllc.com, go to the contact page. We have email addresses there as well as phone numbers. More than happy to talk to any of you if you have specific questions that wasn't covered in the presentation today or projects we can help you with. Also, I did put the link to register for our website in the chat, so hopefully you saw that. Not in the Q&A, but in the chat to register on our website so you can log in and access our assembly selectors. And if anybody else has any other questions, we could stick for another minute or two. Otherwise, thank you all.
Thanks, Mike. Thanks, Steve. Bye-bye.
Thank you, Neil.
Thanks, Neil. Take care, everybody.
Thanks, everybody. Have a great day.